Hey everyone, Jason Sherman here, and today we are honored to be joined by one of the true legends of the space program, Gene Kranz. As NASA flight director during Mercury, Gemini, and Apollo, he was not only at the console for some of our nation's greatest triumphs, Apollo 11, the first moon landing, but also for its most perilous moments, most famously Apollo 13, where his leadership helped bring 3 astronauts safely home. Gene, it's an honor to have you with us, sir.
Great, Jason. It's fine to be with you today. And, it's interesting. You always skip the Gemini 8 mission where we brought the crew down in the West Pacific. It was the only contingency landing we ever had in the history of manned spaceflight.
Wow. I'm glad you brought that up. We can definitely talk more about it. I mean, you are widely recognized as one of the architects of mission control itself. When you look back, what do you feel was your unique contribution to NASA's success?
I believe there's many dimensions to that. I was a military aviator, flew in Korea. So basically, I had a built-in association with the astronauts we'd fly there. I had a team in the flight test team at Holloman Air Force Base. I was flight test engineer in the B-52. And basically, we had a incredible team relationship. We never put anything, our job was to address the challenges of having the B-52 operate in Soviet airspace. So every day we got a chance, we'd sit in the bomb bay, took a look at the new systems we were putting in. Some were very classified in the aircraft, but it was a really team meeting, and we eventually went to the point where we'd be carrying 4 missiles in the bomb bay of the aircraft. And it was a challenge to basically manage not only the B-52, but the aircraft that are flying onto Holloman airspace. So this was a good prelude to working in mission control. In fact, during the course of a mission out at Holloman, we'd work at King 1, which is the range control center. And it had many similarities to mission control. It had a trajectory set of systems you had in there. You had the communications, you had dialogue with other people in the team. So it set a good stage for moving into Project Mercury. At the conclusion of the B-52 test program, basically I applied to work for NASA, and I became a member of the the Space Task Group. And it was interesting. I was originally oriented to be assigned to Goddard Space Flight Center. Huh. And after one mission, Kraft scratched Goddard out from my hiring paperwork, and I became a member of the Houston team.
And during those Mercury days, you mentioned Mercury, NASA was still figuring out the basics of space flight. What were some of the biggest lessons you and your team learned in those early missions?
Well, the greatest challenge we had was, first of all, working with the astronauts. The astronauts were trying to figure out what was the role of this mission control team. What could they do? How could they help me? In the similar fashion, mission control says, hey, we got a spacecraft that is more primitive than the aircraft that I'd been flying. So we knew they needed a lot of help. For instance, they had basically an 8-ball in the center of the spacecraft that represented the Earth. And as soon as they got up into orbit, they would have to rotate the 8-ball as we'd pass over Canary Islands, and we say, now we know we're in Canary Islands, so that would get the pitch axis correct. Then they would have to rotate it to the point where basically they were approaching the continent of Africa down there. So it was interesting. We'd get the spacecraft up into orbit, and we'd say, you're go for orbit. Well, go for orbit? Well, how about go for 1 orbit, or 2 orbits, or 3 orbits?
Yeah.
So that was a real kick. We established our relationship pretty quickly because the crew found out that we had more instrumentation in the ground than they had in the spacecraft.
you and your whole team were working on the ground to keep the astronauts to be successful, and you were the flight director. So that's what, when people hear the phrase flight director, they immediately think about the legendary Gene Kranz. So what did that role actually mean to you personally?
Well, the original flight director role was Chris Kraft. And during John Glenn's mission, we had a problem with, we thought we had a premature heat shield deploy. So basically, the entire management team, Max Faget, Walt Williams, the people from McDonnell Aircraft, were all debating what to do about the thing. And this went on for about 2 orbits until finally we got to the Hawaii station. And when we got to Hawaii, we said, John, we want you to retain, you don't want you to deploy the heat shield after retrofire. We want you to retain the retro rocket on. He says, well, why? And we hadn't told the Hawaii station why. So basically he said, well, they'll tell you that at Texas.
Yeah.
So this was the genesis of the flight director's role. The main job as we finished the Mercury program, one was to establish a highly professional team, have solid technical information and documents for writing the procedures. We had to have a training organization, but we had to establish the flight director's role as the individual responsible for crew safety and mission success.
Makes a lot of sense.
That was Kraft's job. In the 2-year interval between the Mercury and the Gemini program. My job was to build the team, establish the data, and basically establish the functions of the training organization. So we had a team in place capable of flying a much more complex mission than the Mercury was.
Very interesting. And you mentioned that it was the transition from Mercury to Gemini, and Gemini was all about proving what was needed for moon, rendezvous, docking, EVA. How critical was that training and preparation in order to shape Apollo's success?
Without an ability to rendezvous, dock, and perform an EVA, we would have been dead in the water when we started the Apollo program. I think the key thing is, if you take a look at the Apollo program, the first thing it had to do is separate from the Saturn. And then command module would turn around and dock and extract the limb, which required rendezvous. Well, the same thing was true after going down to the surface of the moon, rendezvous. So rendezvous was a critical element there. Docking, related to the rendezvous problem, you also had to dock with the spacecraft. You had to transfer a crew. You had to pull the lunar module out of the Saturn. So basically, rendezvous, docking. The next thing was EVA. And EVA had many dimensions, and it was interesting. One of my jobs in the early Gemini program, I was signed in to become one of the flight directors. Myself and Glenn Lunny and John Hodge were going to join Chris Kraft at the console. And my first mission was scheduled to be Gemini 4. Well, I got called over to Kraft's office, and I expected him to ask, how am I doing, getting ready for this flight director? No, that wasn't the question he asked. He says, hey, it looks like we're going to try to do an EVA in the Gemini 4 mission.
You talked about all the technology that was required in order to make this work and the processes. What was the hardest part in terms of the Apollo mission in particular of preparing the people and the systems to handle the unknown certainty of what might happen?
I think the toughest part of preparing for Apollo was associated with the trajectory team, because this would be the first time that we would leave the environment of Earth and transition to basically a translunar phase of the mission. Then we had a lunar orbit phase, then we had the descent phase, then we had a rendezvous. So we had to move all of the things that we had learned to do in Earth orbit up into deep space, generally in the area of the moon.
Yeah.
This was tough because we were still building our organization at that time. And we had to basically validate what I'd say is the ability to navigate to the moon, operate in the vicinity of the moon, go down to the surface of the moon, lift off, rendezvous, and then basically bring the crew back home. So we're taking the Earth orbital mission and transposing it
Yeah.
up into the lunar vicinity.
And what stands out to you most about the training and simulations NASA used? Like, how close did they come to the real thing?
Oh, the training was, by the time we got to the Apollo program, the technology of simulations and the technology of the simulators was superb.
Mm.
When we would finish our training in the simulators, it was so realistic we were ready for anything that could happen to us in the mission. Now we had a team. The key there was building a training team equivalent to the team in mission control, a team that basically could exercise and integrate the crew in the spacecraft with the team on the ground. And that was a challenge. The early missions, it was we would get into arguments with our instructors and say, that couldn't have happened. And the instructor would simply say, but it just did happen. What are you going to do about it? So it became so real that no matter what problems they threw at us, we had to say, okay, this is real. Let's go for it. And this became very important on many of the Apollo missions because we had, I won't say many problems. The spacecrafts were literally perfect. But throughout the course of each one of the missions, there were small glitches. We'd call them funnies. And we would log every one of the funnies because we did not know for the next phase if that funny was going to impact us. In fact, once we saw a funny early in the mission, it'd have to be with us all the way through the completion of the mission and coming back home. So basically, the business of tracking anomalies forced us to establish what we call SPAN, a spacecraft analysis room. Because as soon as we finished any one phase of the mission, we'd start preparing for the next phase,
Right.
But somebody had to keep looking at the problems.
Yeah.
Was there anything we missed? Anything we should do differently? Did we have to change procedures? So it was always a problem of learning and growing as a team. And then you had 3 teams now, and you had to develop the ability to hand over a perfect handover, not anything missed when you discussed what had happened in the previous shift and what was its impact on subsequent shifts. We broke the mission down into crew awakes, then we had the crew awake, then we had crew sleep. And during crew sleep, we'd work the problem, come up with a solution of problem, then we had a planning shift. So basically, these were the 3 shifts and the teams related to those that operated during the course of a mission.
Super interesting. And during the training, there was a lot of high stress training and high stress testing. How important was things like the centrifuge, for example, in preparing astronauts for missions where failure was not an option?
The centrifuges basically addressed the crew, the environment the crew had to work in during the mission. He had to reach up and touch this switch. Now, generally, the G problem, basically we maintained the G environment only through the launch phase and during the reentry. But it was basically getting to the point where the crew almost blindfolded co-op. Something happened. He had a malprocedures. He had to exercise. He knew exactly where those switches were, what their function was. And this is particularly true when you go to the Apollo 9 mission, and where we had Jerry Griffin had the 9 mission. And at launch, they were hit twice by lightning. And the crew, the spacecraft literally exploded electrically of all the problems that created. Now, we had to very quickly tell the crew what switch to use to restore the telemetry that had been lost, because we wanted telemetry in the ground to help the crew solve the problem. And that was one of the first challenges. By the way, did I say Apollo 9? It was Apollo 11, 12. Apollo 12 was when I had the lightning strike. But it was the simulations. We could not have the kind of success that we had, the time-related response, because generally you work immediately to address that problem, that challenge. Some problems we would say, okay, we'll put the crew to sleep, then we'll work the problem. So it was very important,
Yeah.
the capabilities we had in the simulation. We also use simulation not only to train the crew, but to verify all of our procedures and verify the configuration that we had in mission control.
And there were, where I live in the facilities in Warminster, like the Naval Air Development Center, which is where the astronauts were first pushed to their physical limits before the Apollo, Mercury and Gemini astronauts were here. From your perspective, how important was it for NASA to have that kind of research and testing foundation?
The foundation physically was very important because you had about the G load increased as you were going up through space. The velocity was increasing. So many events became very time critical there. So what you wanted to do is to be able to have a set of procedures readily at hand, and we called them MAL procedures. The MAL procedures readily at hand, the crew was trained in them, and the crew could execute those sets of procedures. The majority of them related to during launch phase. We had several abort modes. We had one abort 1A, but basically would take the crew down on the surface of the Cape. Then we had another one just slightly offshore. Then we had it to the point where we'd have locations in the Atlantic Ocean we'd target for. And then after that, depending upon how much propellant we had in the system and where we were in the trajectory, we had an abort to orbit capability. So we had these very dynamic phases of the mission we went through, and the crew had to be, the mission team had to be, but the crew had to be very timed to respond to that. They had to basically blow off any effects of the acceleration, gravity, loss of gravity, etc.
Absolutely. And you talked about the problem solving earlier. You were mentioning how your team and other teams had to really solve these problems. What made NASA's problem solving culture so unique? And how do you think that started in those early years?
That's maybe the best question we've had so far. I think the thing that I'll go back to the time when I was flying the B-52. I never put anything in the bomb bay of that B-52 that I did not have a hand-drawn schematic of what they did, how it connected to the B-52 systems right on down the line. The major challenge we had in Mercury, we had no set of procedures that related and were technically accurate. So what we had to do is, my job, I was the deputy flight director during the Mercury program. I had a superb engineer by the name of Arnie Aldrich, and I gave him the job to develop spacecraft schematics that showed us everything that we had on board the spacecraft that we needed and could control and use through switches or software. Later on, it became software. Initially, though, it was switches. And the business of building these procedures they were always done by the team on the ground that had the responsibility to basically address the problem with the crew during flight. By the time that we got to the the Apollo program, every procedure, every piece of paper that was carried on board the spacecraft was developed by a controller in mission control. All of the trajectory information we had, all of the flight planning, all of the procedures, normal and emergency procedures, They were all developed by the controller. And this was the reason that during any time we had a problem in flight, we had a depth of knowledge that basically, I won't say exceeded the designers, but was unique to mission control, because a designer will design an electrical system drawing and give it to you. Where the mission controller would say, here's an electrical drawing, but here's how it relates to the instrumentation. Here's how it relates to the controls. So basically, we had integrated schematics that talked the total picture. In fact, our schematic book for the Apollo missions we got into was about 3.5 to 4 inches thick. And every one of those was prepared by the controllers. And when you develop the schematics, then you can write the procedures.
Interesting.
Procedures to support the flight plan. Then you, in case you got a problem, the procedures. So it was really a closed loop that we had. Every time we put a crew on board the spacecraft, the procedures that he carried on board were written by the controllers who would be responding to him in mission control.
Yeah, and the controllers, the astronauts, mission control, all the crew and people on the ground, there was a lot of technology developed. So, for example, at the NADC, they started developing GPS and black boxes and simulators and centrifuge. It transitioned from aviation to spaceflight, right? Because it started out with pilots and then it turned into spaceflight. So, how do you see that kind of R&D contributing to NASA's achievements?
Principal technologies, the first thing is Mercury did not have a computer on board the spacecraft. Gemini had a computer, and basically we had a series of tapes we would load in that computer that provided various information, trajectory information for various phases of the mission. It was only when we got to Apollo that we tried to package everything we needed on a flight inside the computer. And in fact, even this was limited because we did not put procedures in there. There were still paper things. The major challenges we had as the technology involved was related to the computer technology, but I think even more so to communications technology. When we were flying Project Mercury, we had 12 tracking stations around the world that would talk to the crew for up to maybe 1.5 to 3 missions while the spacecraft passed overhead, and that was it. So in the Mercury Control Center, we tried to patch a mission together by 3-minute segments that might have an 8 or 10, sometimes even an hour gap between them to say what was happening in the electrical system. And maybe an hour later, we'd see some more data and we'd try to say, what's the significance of the changes we saw? Well, this also was true in communicating procedures, because we had basically undersea cable that went from the United States to Europe, and then it went from there to radio RF communications to track your stations in Africa, Canary Islands, right on down the line. Same thing, we had a undersea cable that went to Hawaii and then went as far as Australia, but again, it was radio frequency communications from then on. So it was a question of patching the communications in. The communications were really, I think, the key to success in the mission, because when I'm talking communications, by the time we got to the Gemini program, we had digital systems. By the time we got to the Apollo program, we had digital trajectory, communications, and basically data that was dumped to the ground. So it was the evolution of the technology in communications that really allowed us to do the impossible in Apollo.
Well said. And really, the reason why NASA was able to deliver this impossible goal was because the Cold War was in effect, and the U.S. had to invest in aerospace research to beat other countries. Was that really the main reason for NASA's success? Was because of that? Is that why we're not seeing it at such a high level today?
I think the main reason is a good question. I was a Cold War warrior and I was over in Korea, so I didn't like the Russians. Okay.
Tell me how you really feel.
Very straightforward. My goal in space was to beat the Russians. Other people's goal in space was to respond to John F. Kennedy. We choose to go to the moon. We choose to go to the moon in this decade and do the other things. So there was different motivations depending upon the generation of the people that we had in mission control as engineers, as people working in the ranks supporting a mission. So everybody had a different mode. To me, it was I was American to the basically to the point where I bled. My blood was red, white, and blue. And if I go back into the Mercury program, they had a movie that really talked about the B-17 forces in World War II. Okay, and I had a general set of stars in my door, okay, that recognized them. So they called me the general over there. And when we had to move offices and they had to turn around the door inside out. So the door now operated inward instead of outward because my badge would not be removed there. We had a lot of fun. Mercury was a blast to work because that was the growing stage for everybody in this program. Well, everybody had something to contribute.
Absolutely. And you mentioned, being a patriot, and this was a space race against the Russians. So in the 1960s, landing on the moon was more than a technical goal. It was a national mission. So you just mentioned it was a blast. It was a lot of fun. But what did the moon really mean to you and your team back then?
The moon really was the absolute objective that could demonstrate America's technology and their ability to accept risk to achieve great objectives. So it was a combination of several things. The technology was there. The people were willing to accept the risk to get the crew there. And in mission control, after we lost the Apollo 1 crew, basically risk was always on our mind, but basically we became superb managers of the risks of the work that we were doing. We talk about tough and competent. If you take a look on the internet, you'll see what is called the Kranz dictum. That is the set of statements I made after the fire that says we were accountable for many aspects of that failure. From now on, this team will be tough and competent. That is the price for admission to the teams in mission control. So this was more than a set of words. It was a rallying cry. In fact, recently, the book I published was also just recently titled Tough and Competent, because it talked about establishing a culture to achieve complex, high-risk objectives and to live with that risk and be accountable for it.
I love that. You mentioned the tough and competent speech after Apollo 1, which was obviously a terrible time for NASA. Why did that become a part of NASA's DNA? And why do those words still matter today?
I just recently published a book of that title, Tough and Competent. It talks about the relationship that must exist technically and emotionally between members of the mission control team and with the team and the spacecraft. It is a bond that develops. They talk about branding. When I first wore my vest, I branded my team as the white team. And it's interesting, this team seemed to have all the challenges in spaceflight. A Gemini 8 mission, we had the first true mission contingency where we brought the crew down, Armstrong and Scott down in the West Pacific. I was there and my team was there. at the time of Apollo 1 fired. We had done the testing all the day and through the night. We had her over to craft and we were in standby during the fired time frame. There were no easy missions during Apollo. The first unmanned Apollo mission was a unmanned flight of the lunar module. And this flight test basically would set the stage for the timing of all subsequent missions. The computer failed on that. And we flew the spacecraft from the ground and satisfied every one of the flight objectives. We had Apollo 11, which was about as tough a mission. You know, everybody talks about Apollo 12 being tough. But Apollo 11 was split-second, on-the-spot decisions by every member of the team with only seconds to think. Then we had Apollo 13. Apollo 13 was an ultimate test of the entire team, not just my team, but all teams working together. Tough and competent. Tough talks about being willing to stand up and take a position when you must. You know, it's a lot of people are looking for someone else to make the decision, but basically the decision was always in the hands of the controllers. The controllers as individuals and as a team would make a decision. You know, going back to Apollo 13, I had many tough decisions there. The first decision, a good portion of my team wanted to get home the fastest way possible, which meant that we would have to fly in front of the moon. Extremely time critical. No chance for it. And I said, no, that isn't what we're going to do. We want time to identify the problem and develop the capabilities we need. The crew might get cold as a Dickens, but that's tough. Our job is to get them home. And so it was interesting as a team to write a book. This was my second book, and it was a lot more fun. Tough and competent.
I can appreciate that.
This time, instead of having the usual group of people that write the attaboys and the front end of the book, people who write for newspapers and they got the standard attaboy they send. This time here, everyone that reviewed my book faced risk. And it was very interesting. They were all aviators, and they knew what risk was about. When you landed in the hubs, the forward now is talked about the guy who landed in the Hudson with an airplane full of people.
Yeah.
The book was, introduction to the book was written by Andrew Discrepany, which he had on his hands. He was flying an Airbus 380, and he had over almost 500 people in his aircraft. He lost an engine. The engine exploded, blew holes all over the spacecraft. If he didn't get it down, it would be the world's largest airborne aviation disaster.
Wow.
So the people that basically said, hey, this is a good book, were people who had faced risk, so they knew what risk was about.
And when it comes to risk and the moon missions, you know, Apollo, Mercury, Gemini, et cetera, do you think going back to the moon with Artemis missions is still important for humanity's future, or has its meaning changed since the Apollo days?
I'll drop Artemis aside here, but going back to deep space is important.
Okay.
Whether it be the moon and Artemis, whether it be Mars and Artemis, anytime you're moving into a high-risk environment is important to grow the knowledge, the technology, and in particular, the beliefs that as Americans, we are capable of addressing tough systems, whether they be on the ground or in space. I think the Artemis challenge there's going to be two challenges that they got to face. The first one is there's a larger number of players, so integration is going to be tough. The second one, and I worry about that almost as much as the integration, is the interval between missions is going to be very long, maybe a year or more. So how are you going to maintain proficiency as operators and crews? People are going to retire during that period of time. How are you going to maintain the qualities of the team? I think this future missions basically provide a much, a even greater sense of challenge than those that we faced during Apollo.
And, obviously, Gene, you were a legend in the history of NASA and space exploration, but you've also helped preserve it from restoring mission control to mentoring future generations. Why, to you personally, is preserving the Apollo story in the early days so important to you?
I'll go back and say it is extremely important. I flew many of the early jets. I flew the F-86 Sabre, and we had a Sabre Pilots Association. But when enough people died, that association no longer kept living.
Oh,
Our
man.
history was over. The same thing was true of the Super Sabre organizations. In mission control, we continue our history through what we call the AFOA, the Apollo Flight Operators Association. And we still party every July 20th.
I got to come
We
to that
still
party.
drink beer as a team and celebrate the missions and the times, the thing we had together. It is important. History is living. In fact, I'm writing a note to my children right now that I was very angry about the political thing. Yesterday, President Donald Trump, this will probably get me in trouble, but that's okay.
That's okay. Go for it.
President Donald Trump signed an executive order tasking his Secretary of Defense, Pete Hegseth, with established specialized units in the National Guard that will be specifically trained and equipped to deal with public order issues. Well, I was born in 1933, the year Hitler established, the Third Reich.
Oh,
So
man.
I lived when all of those things, we had the brown shirts were Hitler's people that restored the order. And what did Hitler do? He attacked the universities. He attacked the organizations of government. He basically took control of the Fed.
Oh, man.
He had his painting, his portrait hung up in all of the buildings in Germany. So I wrote this note to them. Trump, like Hitler, has now formed the brown shirts to control America's cities.
Well written.
Okay, but I will send that out. We have 6 kids. I'm sure they will say, "What happened? Is he lost his mind?"
I think you're sharp as a tack, sir.
Okay.
And, speaking of future generations that think about Apollo, because everyone still to this day talks about Apollo, what do you want them most to remember about that era and time?
There's several things. We had the national leadership that inspired a generation to do something that many thought was impossible. At that time, you had songs about you can't go to the moon. We had songs about going to the moon. I mean, it was to the point the moon was an object in there that people dreamed about. They wrote stories about. And here we had a man that says, we're going to go there. And John F. Kennedy basically inspired the generation of leaders, engineers, scientists, mathematicians, medical personnel. I mean, there wasn't anybody that wasn't inspired by Kennedy and his speech. He, I won't say drove Congress, but he would not let Congress loose. This is something we are going to do no matter how difficult it is. So I think that as a nation, in order to remain great and continue the direction that we've taken in the past, we're going to have to sign up for tough issues, and I could write another letter to my kids
I bet
about
you
some things that we ought to be doing.
I bet you can, sir. And Gene, one last question I want to ask you that is really meant for everyone listening or watching is if you could leave one message for young people who are going to carry space exploration forward in the next couple of decades, what would you tell them?
There are many things. I will tell them a personal lesson that I learned in a training exercise where I was embarrassed in front of the crew and the entire team. This occurred during Gemini. And the simulation supervisor basically had a leak in the propulsion system. And the flight dynamics officer was trying to say, how much leak do we have and can we get up into orbit? What are we going to do with it? And my team could not make a decision. So I made the decision. And as a result of that bad decision, I put the crew down in the Atlas Mountains and they all died.
Oh, no.
So in front of all of my team and everything else, the sim soup said, why did you make that decision? You should let your team make the decision for you. You are their leader. They should make the decisions you need to do your job. Well, I learned to listen. And nowadays, if you look at any of the real documentaries and any of the space programs, you see me get away from the console. I don't look at my displays anymore. I had the longest headset cord. I could walk from one edge of the room to the other edge of the room, and I would stroll listening. I developed the ability to intensely listen to my people. And I listened not only to the words, but the sound of their voice. I listened to the hesitations they had. Were they absolutely sure about this thing here? So basically, I developed the ability, and if you go back into Apollo 11, anybody had any question, he would have a slight pause in the way he talked. And I'd give him a few more seconds to give a talk, and then it'd go somebody else, and then I'd come back to him. I'd give him a few more seconds to talk. So I think an important thing in today's world is to develop the ability to listen and then make your decision.
Love that. For anyone listening, this is the legend, the one and only Gene Kranz, the Apollo flight director that we've all known and loved our whole lives. Thank you so much. It's been an honor and a privilege to talk to you, Mr. Kranz. Happy belated birthday. We look forward to
Jason, it's been a blast.